right now I'm going to present System 2, DIGIT System 2 Assignment 2. And for our group member, we have 4 group member. First one is me, Victor Lee, and second one, Tao Chun Chuan, third one, Tan Dan Yang, and fourth, Teo Li Ren. And for me and Teo Li Ren, we both going to present Assignment 2, Part 2, application, real application. We're gonna explain the function of our application, the idea of our application, the truth table. And for Tao Chun Chuan, he's gonna explain the waveform, the state diagram, and also the circuit. And for Tan Dan Yang, he's gonna present Assignment 2, Part 1. There's the gray code. That's it.
For question 1, the question is a synchronous counter for a 3-bit gray code number using SR flip-flop. Firstly, we can design the truth table follow the diagram from the question. Secondly, we finish the SR truth table following the formula SR flip-flop with present state and next state 3-bit binary number. Okay, from the K-map, we take the SR result for the example, for result from the truth table with their each column. For example, the S2 equation is follow the similar characteristic from these two circles to form the equation. The circuit is 3-bit sequential logic circuit constructed using 3 SR flip-flop that share a common clock signal. The outputs of the flip-flop are labeled Q2, Q1, and Q0. When together, which together from a 3-bit output. The clear and pre input are used to initialization. When clear is activated, all flip-flop outputs are reset to 0. When preset is activated, the flip-flop output are present 1. From the waveform, the output values follow the state transition according to the clock pulses. Initially, we put the circuit start at state 101. As a clock pulses occur, the output sequence follow the state transition defined in the state diagram. That's all for question 1, part 1. Assignment 2, part 1.
Madam, so right now is Assignment 2, Part 2, sequential circuit application. And for our group, we're going to do walkie-talkie controller. So for our controller, they have 4 states. That is S0, S1, S2, and S3. S1 is on state. It is standby for any mode, transmit, receive, or off. For S1, it is transmit mode. It was sending the message. S2 is receive mode. It's listening to an controlling signal or receive any signal from other walkie-talkie or user. And S3 is an off mode. That means there's no any other mode working. So for output, they have two output right here, Z1 and Z0. For Z1, it's bus. That means in any state, you're gonna bus to let our user know that the walkie-talkie is working, but except in mute state. For Z0, it will be our light. Light is meaning of the light is the walkie-talkie is ready for any state. That means light is the mode for on. Okay, right now I'm gonna explain our truth table. So our next state is rely on our input, and our output is also rely on our input. So this is a millimodal machine. So right now, when this is on state, that means 0, 0. The user press 0, 0, so our next state gonna be 0, 0. So our output gonna be 1, 1. That means the bus is on and also the light is on. Next one, if user press 0, 1, that means S1 state. So our next state also gonna be S1, and so our output gonna be 1, 0. That means bus on, but light is off. For S2 state, that means 1, 0. Next state also gonna be 1, 0. But output for Z1 and Z0, that means bus and light. Bus gonna on, but Z0 gonna off. For S3 state, that's mean mute state. Next state is gonna be mute state, the S3 state. And for bus and Z0, both gonna be off because of this walkie-talkie is already off. Okay, right now I'm gonna let my teammate Tao Chun Chuan to explain the waveform, the circuit, and also the state diagram. That's it for now.
Okay, now I want to talk about my part. So my part, I create this state machine is based on the state diagram. After that, we move to the K-map part, okay? And then I want to talk about K-map JA. So I circle X output in one circle. So the JA equation is X. And then KA, I also circle X output in one circle. There are X bar. And then JB also, the equation is Y. KB, I circle like side to side. So the output is Y bar. And then we move to Z1. Z1, I circle X output in one circle, but I circle two circles. So the equation is X bar OR gate Y bar. So the last one, Z0, I circle 4 possibility or output in one circle. There, the equation is X bar AND gate Y bar. Okay, that's all. And then we insert this output from state diagram at 4 times 4 K-map. So like this, I based on the equation. So I just sambung right. Okay, and then I want to move to the waveform. Wait, we got the circuit waveform. So the clock is up. So input is 0 0. 0 0 is walkie-talkie was on. And then output is 1 1. So 1 1 output is buzzer is activate and the light is on. So the next state is 0 1. So 0 1 is transmit. So transmit, the output is 1 0. 1 0, the buzzer is activate but the light is off. So 1 0 also same like the transmit. 1 0 is receive. So receive also the buzzer is activate but the light is off. Okay, so we move to the 1 1. 1 1 is the walkie-talkie is off. So the state waveform is same, right? Like the circuit waveform and state waveform, the both are same. So this is the correct waveform lah.
The fourth point is the design, the architect, and the model. The design sequential circuit operates as milli-machine because the outputs Z1 and Z0 depends on both present state variable NP and the current external input. The most important is the current external input XY. This is because the external input will directly affect the present state and the output Z1 and Z0. As Victor said, we have on state, transmit state, receive state, and off state. We also have the output logic. Z1 acts as a bus signal and which is active, high, and in any state except the mute state S3, while Z0 is a light indicator signifying the device is ready in any state. We use the milli-machine because our outputs is directly affected by the XY external input. Why we use the Z1 and Z0? This is because the logic for the outputs, it can ensure the users is never in the dark about the device status. Since the bus is active in all states except mute or off, it acts as a heartbeat for the system. It let user know the device is active and not accidentally silent. And the Z0, the dedicated light outputs, confirms the internal hardware is ready for signal processing across all modes. The most vital and most significant in the point of state transition analysis is the sentence. The next state, A plus B plus, is directly determined by the current clock input XY. That means the next state is directly affected by the current input, 2-bit current input X and U. Okay, now I will give some explanation for this design walkie-talkie system. So we put the 2-bit current input XY. This because we have 4 states and we have 2. If we have 2 input, that we will have the 4 possibilities. So we can change the state, any state by state. We can change the input. We can change the next state by our current input. So this is very efficient and the lagging and the time losing is very small. So the third point is the milli model advantage. So we choose the milli model. The factor is milli model unlike a Moore machine where users have to wait for the next clock beat to see a change. The output reacts to the next moment a button only is pressed. So this is because the output tied directly to the input XY. Okay, we go to the point 4, real-world reliability. When we link to the real world, our design is very successful. This is because the user has a visual and audioable confirmation of their device status. User can confirm the device status from the output Z1 bus and Z0 the LED. Okay, next is the discussion. Is the conclusion. In the conclusion, the 2-bit synchronous sequential circuits were successfully designed, and we simulated to function as a control unit for a walkie-talkie application. We use the JK flip-flop to manage our 4 state, transmit state, on state, receive state, and off state. The circuit was implemented as a milli-machine where the outputs Z1 for a bus and Z0 for the light are determined by a combinational present state and the external input XY. And then we have verified the circuit through the quarters 2 simulation. As we have compared the waveform of the circuit and the waveform of the state diagram, both result is the same. Our application proved that the sequential logic can effectively manage the device hardware and ensuring the microphone Z1 and status indicator Z0 respond accurately to user. So this is the all part for the walkie-talkie system. And that's all for the assignment 2. Thank you.